Hello viewers, welcome to the eMath learning platform by Peter Ekaja for mathematics tutorials. I am now going to take you through the continuation of probability theory, and that is to the next type of event, which is mutually exclusive events. This is specifically for the A-level mathematics students. Remember, my YouTube channel is still eMath learning platform, and below are my contact details in case of any questions or clarifications. Remember to subscribe to my channel for you to be able to receive updates whenever I upload new content. Now, for now, let's go direct and look at mutually exclusive events. Now, what do we mean by mutually exclusive events? Now, in this case, we are going to look at a situation where if we have two events, they actually have no element in common. For example, if we have two events A and B and they are actually mutually exclusive, then the set of A intersection B will automatically be an empty set. This automatically implies that the probability of A intersection B is 0. So what does it give as an implication? It also tells you that now the probability of A union B becomes the probability of A plus the probability of B. Remember, it would be minus the probability of A intersection B, but we say the probability of A intersection B is already 0. This is only true for mutually exclusive events. That is a very serious note for you to take seriously. Let's look at some examples. In a race, the probability that John wins is 0.3, and that Paul wins is 0.2, and the probability that Mark wins is 0.4. Find the probability that John or Mark wins. Part B, neither John nor Paul wins. So let's look at the solution for this. But they're telling us to also assume that there are no dead hits. Let's look at the solution. So we are simply going to say that we assume that only one person wins in this case. So it means the two events are actually mutually exclusive. Remember, you're handling a situation of two events. Now, if you look at part A, we are looking at John or Mark. Now, the probability of any of them winning is just as good as the probability of John winning plus the probability of Mark winning. So you simply substitute and add up the 0.3 plus 0.4 to give you 0.7. Then part B, they want the probability that neither John nor Paul wins. What do we do here? So remember, the probability of winning plus the probability of them not winning is actually 1. Meaning, if we want the probability of all of them not winning, we get the total probability minus the probability of any of them winning. So that is why we are now going to say 1 minus 0.5. Why do we say 0.5? We have simply added the probability of John winning together with the probability of Paul winning. Because if you get back here, if you get back to this point, we had each of their probabilities at 0.3 and 0.2. So if you add them, it gives you 0.5. So allow me proceed from this point now. Allow me proceed from this point. So we have looked at part B already. So we can now substitute. Then if you subtract this, it gives you 0.5. Now, if you continue to the next question. So our question 2 says events A and B are mutually exclusive, such that probability of A union B is 0.8, probability of A is 0.4. Find part A, probability of B, part B, probability of A intersection B complement, part C, probability of A complement intersection B, then part D is given as this, and part E is given as that. Let's look at the solution for this. Let's look at the solution for this. For part A, we are saying from probability of A union B equals probability of A plus probability of B, which we quoted clearly that this is only true for mutually exclusive events, which are simply substitute the union, the probability of the union, the probability of A, and we shall be able to get the probability of B by subtracting this from this. That gives us the 0.4. Let's look at part B. They wanted probability of A intersection B complement. Now from set theory, you realize that the probability of A intersection B complement is as good as the probability of A minus the probability of A intersection B. But remember, this is already 0 because we said these are mutually exclusive events. So it means we shall simply substitute for 0.4 minus 0. And that gives us 0.4. Let's look at part C. Part C wants the probability of A complement intersection B. By set theory again, this is as good as probability of B minus probability of A intersection B. But this is still 0, and we know this already as 0.4. So it will also be 0.4 minus 0, and that gives us 0.4. Let's look at part C together. The next part, actually part D, which says probability of A complement intersection B complement. Now, by De Morgan's, we said probability of A complement intersection B complement is the same as the probability of A union B but complement, which can be written as 1 minus probability of A union B. And if you substitute for this was given in the equation as 0.8. You will simply get this minus 0.8, which gives us 0.2. If you go on to the next part E, they wanted probability of A complement union B complement, which still by De Morgan's is the same as probability of A intersection B but complement. And that will be 1 minus probability of A intersection B, but we all know that this is 0 since the events are mutually exclusive. So when you subtract, you come up with 1. So let's look at question 3 now. It says events A and B are mutually exclusive such that probability of this is that, probability of that is that. Find Roman 1, probability of B, Roman 2, probability of A, Roman 3, probability of A intersection B, Roman 4, probability of A intersection B complement. What did we do in this case? So let's look at the solution. So part A, from set theory again, this is very true. Probability of A complement intersection B is equals probability of B minus probability of A intersection B. Substitute your values. We already know probability of A intersection B is 0, and we knew this already. It was given in the question. So you simply get probability of B as 0.3. Roman 2, this now, if you compare this with probability of A union B, the formula will just be the same, only that wherever we have A, we shall have the complement sign indicated. So it will be probability of A complement plus probability of B minus probability of A complement intersection B. And if you do the substitution, you will realize that you're looking for probability of A, but you had probability of A complement. But remember, it is as good as 1 minus probability of A. And if you do this substitution, you realize that if you make probability of A the subject, it will give you 1 minus 0.45, and that automatically gives us 0.55 as Roman 2. So you realize things are actually very easy. Roman 3, they wanted probability of A intersection B. Here we are confidently concluding that it is 0, and we are giving a reason. Why? Because they are mutually exclusive events. As simple as that. So let's look at Roman 4. From set theory, this is again probability of A minus probability of A intersection B, but this is already 0. So should you substitute your values, you realize that we have 0.55 minus 0, and that finally gives you 0.55. So if you look at that, you can now try out the following trial questions. So number 1 is given clearly as that, and number 2 is given clearly as this. So from this point, try out this exercise and check on yourself. In case of any question, I'm always there for free consultations. Have the best of your day, and please remember to subscribe if you have not.